Good afternoon. Thanks for the kind introduction. It's my honor to be here to introduce our recent study on security analysis of Ethereum and its smart contracts. So since Bitcoin's inception and Ethereum's introduction of smart contracts, the blockchain ecosystem has grown increasingly prosperous. Unfortunately, the blockchain ecosystem are not as secure as what we expect, with many blockchain platforms and smart contracts being prone to vulnerabilities as well as different types of attacks. One of the reasons may be this catchword in the blockchain community, code is law. But can we really follow it? The answer may be no. Because you may expect that the code is bug-free and has been fully audited. Unfortunately, there are many known or unknown vulnerabilities in blockchain platforms and smart contracts. You may assume that the blockchain infrastructure are secure and robust. However, existing blockchain infrastructures may be prone to attacks. And there are some other inconsistencies between the ideal case as well as the reality. To address this, so this slide shows the major components in the blockchain ecosystem. Users using the front end interacting with the layer 1 or layer 2 or layer n infrastructures via the internet. Applications written in smart contract running on top of these infrastructures. You may wonder which part will become the Achilles heel of blockchain ecosystem. Our research showed that every part could be potentially the target of attacks. So my research intends to develop a holistic approach to safeguarding blockchain ecosystem from two aspects. One is to protect blockchain infrastructure applications in smart contract, front ends, and network by identifying zero-day vulnerabilities, developing new tools and algorithms to identify those vulnerabilities, as well as helping developers fix those vulnerabilities. The second aspect is to detect new attacks, detect malware, as well as protect blockchain applications from attacks. So today I will focus on the first aspect. In particular, I will first introduce our recent study on a new type of denial of service attack on blockchain using the MPT. So thanks, Li for introducing the gas mechanism as well as the fee. So Ethereum used the execution fee to prevent resource abusing. Unfortunately, there are still many DOS vulnerabilities in Ethereum as well as other similar blockchain platforms. For example, the denial of service attack just mentioned by the Li, as well as these two DOS attacks exploiting the underpriced opcode. The fundamental issue lies that the gas cost is not equal to resource consumption. So we did a comprehensive measurement on the gas mechanism and found that the gas cost is not properly set, and there are underpriced opcodes that can be exploited to launch denial of service attacks on Ethereum. Later, we found that this issue could be exploited to launch denial of service attack on RPC service, which is crucial for connecting the front end and back end of decentralized apps, or dApps. The paper appears in NDSS 2021. Although RPC service is crucial, it is less decentralized than the blockchain network, making it a potential single point of failure in the presence of denial of service attack, which could jeopardize the whole dApp ecosystem. Basically, we identify a vulnerable service API, the ESEC core. User can use this API to estimate the gas consumption. But attacker can exploit this API to call smart contracts that will consume lots of computational resources, like a function having an infinity loop. By doing so, the attacker can effectively stop the node from executing critical operations for all the dApps, like BOCHK and transaction synchronization. So if you are interested, you can refer to our paper. So today I will introduce a new type of denial of service attack targeting on blockchain state storage. So this paper will appear in IEEE Security and Privacy, one of the top security conference next month. Let me first introduce some background knowledge. Blockchain state storage is usually managed by a structure, for example, MPT. And a leaf node in the MPT stores the value of the persistent data. All intermediate nodes from the root to the leaf node correspond to the key of this value. The basic idea of this new attack is to strategically introduce many more intermediate nodes into MPT, compelling blockchain to use more resources for state maintenance and validation, thereby degrading its performance. It's worth noting that, unlike previous denial of service attack, there are limits to the duration of the attack. This new type of attack will persistently aggravate the resource consumption for state maintenance as well as the updates. So this figure shows give an example of the blockchain state storage. We have the account data storing all accounts information. There are also the contract data containing the persistent data of each contract. And the index, for example, this ACD3F is used to leave a leaf node in the MPT starting from the root. And there are three types of nodes in the MPT structure. One is the branch node, extension node, and the leaf node. So if you are interested in the details, please refer to our paper. Then let's see what will happen if we insert a new leaf node into MPT. Basically, for example, we insert a new leaf node, 111D1F3, into MPT. The original leaf node, 1F, 12F, will be split into 3 nodes: an extension node, a branch node, and 2 leaf nodes. It's worth noting that all those node manipulation, insertion, and deletion will lead to significant resource consumption. Then I will introduce 2 observations that guide us to identify this new type of vulnerability. The first one is the flaw of the gas mechanism. Let me use an example to explain this flaw. So in this MPT, there are 3 accounts, AAB3E, ABC60, and ACD3F, as well as 2 transactions. The first transaction is to transfer Ether from AAB3E to ACD3F. The second one is to transfer Ether from AAB3E to ABC60. According to Ethereum specification, these 2 transactions will cost the same amount of gas. However, the resource consumed by these 2 transactions are different, because the first transaction will involve 6 nodes, will modify 6 nodes, but the second one will modify 9 nodes. They lead to difference in the resource consumption. The root cause of this flaw is that the current gas mechanism does not consider the exact resources consumed for maintaining and verifying the state in MPT. And the second observation is related to the heavy burden of state maintenance. Most operations with MPT are the major performance bottleneck of blockchain. Recent studies show that more than 80% of blockchain execution time was spent in interacting with MPT. And we also observed that the time required for interacting with MPT increased linearly with the number of the involved nodes. Then with these 2 observations, we can decide a new type of denial of service attack on blockchain, on Ethereum, as well as all blockchain platforms using MPT for state storage. The basic idea is to strategically introduce more intermediate nodes. So we designed 3 strategies for increasing the nodes. For example, we can split a node into a leaf node and a branch node. Or we can split a node into an extension node, a branch node, and a new leaf node. And we can also replace an extension node into a branch node and a new extension node. So I will skip the details. If you are interested, please refer to our paper. So here I will report some evaluation results. So we first evaluate the impact of this attack in the fork of Ethereum. By manipulating 10,000 blocks, we can introduce 1.11 times of new intermediate node into the MPT. In this case, Ethereum has to spend more 111% resources to handle those nodes. And it's worth noting that for all future transactions involving the nodes added by Nergo, the time cost of their state modification is persistently raised. We also launched the attack in the testnet of Ethereum and BSC. And you can see that the nodes involved, the number of nodes involved for updating a node also increased significantly. And in this case, both blockchain platforms have to spend much more resources in handling those nodes. So for this part, the takeaway is the gas cost is not equal to the resource consumption. We identified a novel attack and a new attack service. Then I will talk about our recent work on how to speed up vulnerability discovery for smart contracts. Fuzzing is a widely used test techniques for vulnerability discovery. Basically, you will generate a set of randomly input in order to trigger potential vulnerabilities or exploitable bugs in the target program or smart contracts. We recently performed a comprehensive empirical study on existing fuzzers for smart contract and identified a number of interesting observations and insights. So the paper will appear in ESEC, one of the top software engineering conference. So these are the fuzzers we evaluate. These slides list some of the observations. For example, existing fuzzers are far from satisfactory in terms of vulnerability discovery. We also have a set of observations related to the fuzzer throughput. For example, the speed of vulnerability detection is largely influenced by fuzzer throughput. The quality of initial seed and the fuzzer throughput are critical for quickly reaching the high code coverage. Moreover, using standalone EVMs can significantly improve the fuzzer throughput. Okay, given this insight, a natural question arises. What would be the bottleneck of fuzzer throughput? So we performed a study, and we found that the EVM execution is the major bottleneck of fuzzer throughput. So for example, we evaluate 2 SOTA fuzzer, ITY fast and Smart 10. And our result shows that more than 80% of total time was spent on EVM execution. Moreover, the more complex the smart contract is, the more time spent on EVM execution. Then how can we decrease the EVM execution time? The task parallelism would be a straightforward yet costly approach to improve the fuzzer throughput. For example, you may use a cluster of computers and then run the fuzzer in order to identify the vulnerabilities. However, the cost would be quite high if you want to use a cluster of computers. Our solution is MAO, the first GPU-based fuzzer for smart contract. So this paper will appear in IEEE Security and Privacy, one of the top security conference. So our approach leverage the GPU's parallel computation power as well as the feature of smart contract faster to boost the faster throughput. It's non-trivial to develop GPU-based faster for smart contracts due to many challenging issues. You may refer to our paper for all the details. So here I will just mention one. GPU was not designed for general computation. To address this issue, we turned the smart contract fuzzing into a GPU-friendly application to let it be runnable on GPU. So this figure shows the architecture of MAO. It consists of 3 major components. Transformer will lift the EVM bytecode to an LLVM assembly. Vector will convert the LLVM instruction into vector operations because GPU can only support those vector computation. And we also generate a SIMD program to track the smart contract execution state in GPU environment. And later, in the code generation phase, we will use the LLVM backend to turn the vectorized LLVM assembly into PDX code that could be executed in the GPU. The evaluator will schedule and evaluate a batch of Cs in parallel to improve the fuzzing throughput. So I do not have time to introduce all the details. If you are interested, please check out our paper. Here I will just present some evaluation results. So MAO outperform all baselines in terms of the code coverage. And you can explore much more distinct instructions than different baselines, in particular for those large smart contracts. And our approach is much faster than baseline. It can achieve around 10 times improvement in faster throughput. And it's also much more cost-effective and energy efficient compared to the baseline. It's worth noting that it's easy to schedule thousands of GPU cores than scheduling thousands of CPU cores, right? And another interesting observation is this one. In a recent paper in FSC 2020, Marco and Brandon found that finding new bugs with fuzzing needs an exponential increase in the number of computational resources. And our result is consistent with this observation. But it's worth noting that it's much easier to schedule thousands of GPU cores for fuzzing smart contracts. In terms of bug detection, MAO is more effective than baseline in terms of the accuracy of bug detection, in particular for those large smart contracts. And we also apply MAO to real-world smart contracts and identify a number of vulnerable projects. In particular, around 120 bugs can only be found by MAO rather than other baselines. So the takeaway for this part is that we present the first in-depth study of the existing smart contract fuzzers. We have many interesting insights and observations, and we also propose the future research direction. And in particular, we developed MAO, the first GPU-based fuzzer for smart contract. It's much faster than existing fuzzers. So in conclusion, the widespread vulnerability in the critical part of blockchain ecosystem compromise its security, calling for more and more research and development to address these issues. Last but not least, so PolyU has a very strong team of researchers and students working on blockchain technology. The university has established the Center for Blockchain Technology and launched the first MSc in blockchain technology in Hong Kong. So we are open to more academic and industry collaborations, and we are committed to nurturing talents in blockchain technology. That's all. Thank you so much.